So let's talk through the questions. So this first question, the way I designed this one was basically as a fancy way of doing matching. I wanted to see whether you knew different terminology. So basically you needed to know 5 or 7 different definitions and what they mean. So before I even go on to answer the question, can we just talk through these 7 different definitions up here? And just make sure you know what they are. So what does a heterogeneous mean? Do you have something? Sure, something that's different. You should visibly be able to see differences. And that's what hetero means, different. Homogeneous or homogeneous means the same. Make sense? What's a solute? You know what? That's perfect. We can take both definitions at once. A solute goes into a solvent. There is less of a solute and more of a solvent. They're the two things that go together. Does a solute have to be a certain state of matter, by the way? No, but typically for our purposes, it's almost always going to be solid, but it doesn't have to be solid. Agitation, that's a fancy word for stirring, good. And then stock and standard solution. I feel like most people probably got these definitions a little bit mixed up maybe. So a stock solution is a highly concentrated solution. Like for example, in the orange juice analogy I had, if you make orange juice from like the frozen stuff that you put in your freezer, that's a stock solution. It is concentrated. If you try to eat it, you're probably going to get sick because it's pretty thick. Does that make sense? A standard solution then is a solution in which you know its concentration. Like you know its concentration very exactly. Like it has a concentration of 1.03257 moles per liter. Does that make sense? So knowing those 7 definitions, let's fill in the blanks. I basically wrote a sentence here. If you want to create a solution using the dilution process, there's a keyword there. If you're diluting stuff, you need to dilute stock solution. You need to use the really concentrated stuff to make it less concentrated. In order to do that, you need to add more solvent because you're adding more of like the liquid. In order to disperse particles, you need to stir, which we just said was agitation. And then if you stir this all up, it should probably look the same, so that would be homogenized. I'm guessing most people, over the years, they usually get the number 6 one wrong. Is that right? Most of you? You pick the wrong number? Okay. This is a really clever question design. Really, it's 4 questions in one, isn't it? I really asked you to know 4 different terms, but you need to get all 4 right in order to earn the mark. So even if you got 3 out of 4, you missed it. Does that make sense? The next one. So this one, it says number 2 in the corner, but I reordered my questions one of these years, so this is actually the first multiple choice one. So reading this, it says, which of the equations represents this guy right here being ionized? So let's just talk a bit about the word ionized. Or what does the word ionized mean? Or how about this? What sort of things get ionized? Good, molecular things. More specifically, acids. Acids get ionized. Because acids have molecular bonds, and they should not break into pieces. Ionic things should break into pieces. They dissociate. So we need to try to figure out where this guy right here is being ionized. And as I look through, this one right here, the acid is written as a product. So hopefully you're able to narrow that down and say, that doesn't make sense. We should be starting with the acid and breaking it up. So that one's out. And even C right here doesn't even involve that acid, so C is kind of nonsensical as well. Does that logic make sense so far? So hopefully you're down to A or D. And one of the things hopefully you recognize about acids is that acids involve H+, or possibly H3O+. And yeah, both of them involve that. But this guy right here throws in a base for some sort of odd reason. But acids don't make hydroxide, do they? So that kind of rules this one out here. This is the way we would write something being ionized. This H right here is going to break off and attach itself to the water, forming this compound here. If you've forgotten, it's called hydronium. Hydronium. The example I like to give for hydronium is that it's a water molecule with an extra H+. Do you guys remember what H+ is? proton. Does that make sense? Hydrogen as an atom has 1 proton, 1 electron. Very small molecule. If you rip off the electron, it's merely a proton. We're talking like one of the smallest units of matter we can find. And that proton by itself is not very stable. So often it nestles itself into a water molecule, and like collectively it makes this H3O+. That makes sense? Okay. Stop me if I lose you. I'll just keep moving on then. Okay. So back to knowing a definition then. Homogeneous. Homogeneous means it needs to look the same. You should not be able to visibly see differences. Orange juice. Well, I would say orange juice, you probably won't see a difference. But what if there's extra pulp? Now will there be differences that you can see in the orange juice? Alright, so that's out. Raisin bran. Raisins and bran. You can see the differences, right? Sand and rocks. You should be able to see the difference. But steel just looks the same. It's, you know, just one color all the way through. Does that make sense? Okay. Okay, here's a question where the solution to it is very simple, but you have to understand what I'm asking you. Okay. We're going to have some iron 3 hydroxide. So the first thing I need to be able to do is figure out what iron 3 hydroxide is. Anybody know its formula? Good. The OH being in brackets, but yeah. That's iron 3 hydroxide. And it asks what the concentration of the iron 3 ions are. And it asks what the concentration of the hydroxide ions are. So by virtue of it being an ionic compound, it's probably going to dissociate into pieces just like this. Only I've missed one thing in this equation so far. Anyone see what I've missed? But it's not balanced. What do I need to balance it? Good job, Michael. Yeah. So in a way, you probably need to kind of write out a dissociation equation. That's probably one of the first things. You have a solution of iron 3 hydroxide. You've got the iron 3 ions. You've got the hydroxide ions. Now let's put some numbers on this. This solution was 0.5 moles per liter. I have an analogy for this, and I hope this analogy makes sense. My daughter, she plays with a big Lego toy. In my room, there is one Lego toy, but then she rips it into pieces. What happens to the concentration? Concentration will go up. Even though we haven't added new stuff to the room, it used to be like one Lego toy per room, and then she rips all the little pieces into little pieces, and now there's 12 little pieces in the room. Does that make sense? So the concentration will go up. How much will it go up by? Well, if this is a 1 and this is a 1, this guy's concentration will be the exact same. But if this guy right here is a 3, its concentration will triple. So take half and triple it, that makes it 1.5. So like from here to here, times by 1. From here to here, though, times by 3. For some reason, your guys' test formatted really weirdly, but the only one that fits that is CETA. Does that make sense? Out of curiosity, who got that on their own?
I got it, but it was a step.
Okay. So there'd be another good reason why I want to go over something like this, is maybe you took an educated guess at it. But hopefully now you know the logic behind it. That's one of the reasons why I like having that little bar in the middle there. I mean, if you guess and you get it right, it's worth it, I guess. If you guess and you get it wrong, don't forget it is taking away a part of a mark. So sometimes it may be better, actually, just to not answer the question and say, I don't know it. And that's okay that I don't know it, because I'll learn it later. Any questions? Okay, math question. This one asks us for weight over volume, or at least it involves weight over volume. Do you guys remember what weight over volume kind of means?
Grams per liter.
Yeah, it's like a grams per, in this case I think it's grams per milliliter, but so really this 11% really means 0.11 grams per milliliter. That's kind of what this notation right here means. So I took the 11 and I made it 0.11 because that's like how a percentage works. So, okay, I've only got one other number. I have 355 milliliters. But maybe you can visualize this. If I take the 355 milliliters and I multiply them, can you visualize how those units cancel? So basically you just need to take 0.11 and times by 355. And I got 39.05 when I did that. One last thing, we got to get sig digs right though. How many sig digs should you have? 2 is correct, yeah. Why?
Because of the 11%.
Good job, yeah. The 11 right here means 2 sig digs. So if you tried to write out 39.1, you shouldn't have given yourself credit for that because you have the wrong number of sig digs. The right answer should have just been 39 because those 2 will come off the end. By the way, for context, that's terrifying how much sugar is in a can of pop. Think about that for a second. If it actually is 11% weight over volume, and this is just like a regular little can of pop, that's 39 grams of sugar in there. Anyone ever seen like some YouTube videos where they like take pop and they like boil it off and stuff like that? Anyone ever seen like one of those on Facebook or Twitter or something? It's disgusting how much sugar is in carbonated drinks. Like it's a lot. Which is a research topic, by the way, for your research paper. You can look into that. Anyways. Questions on this one? All right, moving on. Okay, this one. This is a challenging question. Does anybody feel comfortable with their answer so much that they got it right, they can explain to the group how they chose their answer? Okay. So I got a question then. Why'd you pick an answer? Why'd you guess? Because I was going to make you go down a quarter mark. You know what I mean?
If you leave it blank, you go down.
Well, so how it works is that if you leave it blank, you don't go up or you don't go down. That makes sense? But if you get it wrong, then it's taking marks away from you. That makes sense? So like this might be a good question where, I mean, I know everything you've been taught for the last 10 years of your life has said, if you don't know, guess. I want you to change that line of thinking and say, if you don't know the answer, you might have gotten it right because you just randomly took a stab at it. But is that actually learning? Do you actually know what you're talking about? You can say, well, I guess you know you don't. And my goal is I want to help you figure out how to learn. That makes sense? So this is a challenging question, by the way. There's a lot to this one. Do you guys have your periodic tables nearby? Can you guys find the solubility chart on page like 5 or 6 or something? You guys know this one right here? This one here. Can you guys find where copper bromide would be in that chart? You know, like where you get all these boxes, and then the top one is aqueous, and the bottom one's solid, and bromine is like in one of these columns here. Where does it fit? Yeah, the copper plus with the bromine goes in the slightly soluble. However, there's a piece of information there that, I mean, we haven't used a ton, but there is a number that goes here. It is 0.1 moles per liter. And it actually says it has to be less than that. You guys remember talking about that, even just briefly in class? That means that this thing right here, its maximum concentration, at the very best, would be 0.1 moles per liter. If you try to make it go past 0.1 moles per liter, will stuff dissolve? No. So like think back to our lab. At this point here, you're shoving so much solid into your little test tube that the only way you can get it to dissolve is if you increase the temperature. Right? It is so past its capacity that therefore it must be oversaturated. Does that logic make sense?
Yeah.
And I would say that that's the kind of question going forward where you probably have those skills. I'm hoping that's something you knew, right? Like you knew that there was a table. You knew how to use the table. I'm guessing what most people forgot is that there is a number on here. And that number could be useful in solving that question.
No, I was just being stupid and thought it was saturated.
Does that make sense? That's a very high-level thinking kind of question, by the way. Right? Like that's not something that most people get right off the bat. Right? Where it's like we had to use multiple pieces of information that you knew and piece them together to try to solve this puzzle. Hopefully no one picked uber saturated at the very least. You picked uber?
Yeah, I know.
Okay. Fair enough.
I don't know. I was just being stupid.
Apparently. Okay. Actually, you know what? That leads me to another point. I've said this in math a lot. It sounds harsh, but you need to not make dumb mistakes. I don't have a solution for that where I'm just like, here, drink this and you'll stop making dumb mistakes. But at the level that I'm trying to help you guys get to in our math and science here, you can't. Does that make sense? Because it's hard enough on its own that the ones that you know, you can't get those ones wrong. Does that make sense? So, I don't have a solution to that other than like care and attention to detail. Okay, number 7, or whatever the number is for you guys, I know it's out of order, is just a knowledge thing. I had a slide on it in our notes. POP dissolves gas inside a liquid. And you can actually dissolve more gases if you change the temperature. But it's not increased temperature, it's decreased temperature. So hopefully you just knew this. If you dissolve a gas in a liquid, you actually want lower temperatures. If you don't remember the reason why, the reason is that gases at higher temperatures, gases expand. Does that make sense? And so if you have a high temperature, gas will take up more room. That means you can't dissolve very much gas. But if you shrink the temperature down, the gas will contract. And so if you use a low temperature, you can shove more gas inside of a solution. Out of curiosity, anybody get that one on their own there? Okay, good. Whichever one the gas and liquid one is. I would say this is the kind of question where, I don't want to be harsh, but you have to be able to get this one here. Because there really wasn't much to this question other than we talked about it in our notes, and you don't really have to interpret anything. You just had to know the answer. Does that make sense? Okay, lab type question. This is the key word here. I want to talk about the word accurate. What does accuracy mean? Yeah, using it correctly. You have to, if you're using a piece of lab equipment correctly, that contributes to its accuracy. If there is a line on a piece of lab equipment and you go past that line, you've used it incorrectly. Does that make sense? So when you make a standard solution, I made a standard solution in class where like I went to the scale, I weighed out some stuff, we put it into a volumetric flask eventually. Does that make sense? One of these things is not really relevant, and it's the beaker. What do we use a beaker for when we make a solution? You guys remember? We use the beaker purely so that we have a container that we can stir crystals in. That's it. Because usually we make it inside the volumetric flask. The volumetric flask is the really long, thin guy that has like the ball at the end there. This is the volumetric flask. The problem with that is that you can't stir stuff inside a volumetric flask. The stir stick is just too thick to fit down here. So before you do that, you take your solid crystals, you put them in a beaker, you add some water, and then you stir in here, and then you pour it into the flask. So do you actually need to use the beaker for any measuring whatsoever? No. Does that make sense? Okay. CO2. Tell me something about CO2. Sorry, go ahead. Okay, so that's its name. What else do you know about CO2? Sure, it's a gas. We breathe it out. Okay, talk to me about how it bonds. Good, there's the really key here. This is a molecular bond. Do molecular things have the ability to dissociate? No. Acids can ionize, but it's just an acid. Okay, so CO2 cannot break up into positive and minuses. Does that make sense? So therefore, should it be able to conduct? Not at all. It should not conduct well, if at all. Because how do things conduct? They need to have positives and negatives. Ionic things conduct. CO2 gas does not have that ability. It bonds molecularly. Does that make sense? Okay, let's do a math question. This one is probably the most straightforward of all the math questions we have. You have to be able to interpret what I'm asking for. I asked you for capital M. What does capital M mean? Which is what units? Good, moles per liter, yeah. Capital M, molarity, means find moles, divide by liters. This one is about as straightforward as you can get. We have moles. We have 0.2 moles. We just need liters. We don't have liters. We have milliliters, though. How do you convert liters to milliliters and back and forth? Yeah, you either multiply or divide by 1,000. You just got to make sure you don't do the wrong one. In this case here, you're going to divide by 1,000. So this is what your math should have looked like. This many moles divided by this many liters. Basically, take the two numbers and divide them. Okay, so my calculator spits out this number here, etc. How do I answer this properly, though? You gotta get your sig digs right. So how many sig digs do I get? 2, yeah. This guy right here gives you 2 sig digs. The 2 and the 0 both count. So there, that's 2 sig digs. I will give you a little bit of leeway on your rounding. The diploma exam at some point probably won't, but this shouldn't be 0.26 because this 6 right here would round it up. So the correct answer is 0.27. Does that make sense? I would say of all the math ones, that one's probably one of the most straightforward. There's not a lot to do other than just divide the two numbers. I started off with a fairly simple one. Because here is another math question, and it's not quite as straightforward. There's a few more steps here. First, it talks about copper 2 nitrate. So before we do anything, it's probably likely that we need to know what copper 2 nitrate is. This is why we spent 2 full weeks doing Science 10 review, because if you can't figure out what copper 2 nitrate is, you're going to script the question. So, anybody know copper 2 nitrate's formula? Cu with a 2 after the NO3. Good. That is one of the most critical pieces, because if you can't figure out its formula, when we do its molar mass later, we're going to be screwed. So you got to make sure you can write out copper 2 nitrate's formula. We're looking for grams. These numbers right here, if you can kind of see putting them together, 12.0 liters and 0.150 moles per liter. If I put them in this orientation, hopefully you can visualize, say, look, the liters cancels. That's helpful. But it's not what I want. I want grams, and the unit that I have left right now is moles. So I need some sort of way of converting moles to grams, and that's where molar mass comes in. So I need to find this guy's molar mass. So I believe copper is 6355. Nitrogen is 1401. And you need 2 of those. And then oxygen is 16 right on the dot, and you're going to need 6 of those. Anybody else get that? Okay, good. Thank you. Does that make sense to everybody? So now the key is, how do we put all of these numbers together? We have a liters, and that cancels with this liters down here, so that's useful. We have a mole. I don't want this mole sitting right here. So I'm going to put a mole symbol on the bottom, and yeah, it's gone. I want grams, so I'll put grams on top. This number right here goes with grams, so I'll put the 187.57 right here. So liters cancels with liters. Moles cancels with moles. I have a grams number. So we just need to calculate it right now. I got 337.626. Last step, get the sig digs right. I get 3, so that makes it 338. Brief aside, I would say that in my experience as a teacher, I can tell how well students do on their tests just by looking at numeric response. If you know what you're doing, you'll get numeric responses correct. If you don't know what you're doing, numeric response, you have no shot at guessing, right? Like, you're just wildly flailing around trying to pick numbers. Does that make sense? I don't know that that means that you need to spend more time on your numeric response, but I find that, I mean, that to me is the indicator of how well you did. I would say if I looked at people's tests, if you happen to get, like, say, 6 or 7 numeric responses right, you probably did better than people who, I mean, and on multiple choice too, right? Than people who didn't. So they're tricky, you know, because you can't guess. Does that make sense? at some point, we're a long ways off, but at some point I'm hoping I'll teach you Chem 30. At the end of Chem 30, you got that mean old diploma exam. If you want to do well in the diploma exam, I've discovered you have to be able to nail the multiple choice, the numeric response, because there's 16 of them. There's a lot of numeric response when you eventually get to the Chem diploma, and that I've discovered is what separates the decent marks from the good marks, is if you can get those 16 numeric response. Because, I mean, anyone can guess A, B, C, D on the rest, and unlike me, they won't penalize you, so you may as well just guess, right? But you can't guess on the numeric response. I guess you can, but what are the odds of you getting it right? On the numeric response?
Yeah.
Buy a lottery ticket. Okay, let's do up till question 15, at least on here, and then we'll take a break. Does that work? Okay, this is basically a definition. You just need to know the definition of ionic things dissolving is dissociation. Good. Because there's not a lot I can add to that. Either you knew it or you didn't. Ionization is for covalent things. Okay. Another math question. This one right here, you need to know what a part per million is. A part per million is a milligram in a liter. So if you knew that, that's good. Now we need to be able to apply it as well. That's a key word, apply. Take the knowledge you have. We're looking for milligrams as our units. So it sure would be nice if we could find a way to cancel out this liters by timesing by some sort of liters number. But this is in milliliters. So it's divided by 1,000. I'll put it in liters. So this number right here, if you divide by 1,000, is 0.5 liters. Times those two things, you see how the liters cancels? The only thing left is milligrams, which is what we wanted. So basically you need half of 1.5, which is 0.75. Speaking of this question, another research topic that you could do if you wanted to is researching how fluorine gets added to our drinking water. And that's what this one right here was. It's kind of talking a bit about how you shouldn't have too much fluorine in your drinking water. That's not safe, but a low amount, like 0.75 milligrams is a very small amount. Like my scale cannot even come close to registering that. All right, let's do two more and we'll take a break. This is a fairly challenging question. You have to be able to interpret what the heck this diagram is talking about. And you need to have this table right here. Because that's what it's kind of referring to is, do you know how to use this table and interpret things? Does that make sense? So I'll do my best to try to look at the table and talk back and forth because I don't have more than one slide here. But we want to try to figure out what the unknown cation could be. So there must be a positive ion in all of these things here. And in two of the beakers, it does form a precipitate. And in two of the beakers, it doesn't. So I'm going to walk through all four of these choices and see whether it works. So let's see whether it's Pb2+. What would happen if Pb2+ went with CO3? So looking in my thing here, CO3, Pb2+ would be in the bottom category, which means it would be solid. And look, there's a precipitate. So that makes sense if it was Pb2+. But I got to try the same Pb2+ in all of them. What happens with Pb2+ and SO4? SO4, Pb2+ is solid. This guy right here wasn't solid. So it wasn't lead. Does that make sense? So on to the next one. Let's try strontium. Strontium 2+. So CO3 and strontium. CO3, strontium is in the most category because it's not in group 1. So that actually fits for strontium. And then SO4, again, strontium is in the bottom category, means it should be solid. But clearly this diagram shows that it's not solid. So strontium doesn't fit either. So that one's out. Does that logic make sense so far? So try the next one. Let's try iron 3+. Iron 3+ with carbonate. Carbonate, again, goes with pretty much everybody in the bottom category, so that should be solid, so that fits. SO4, iron 3+ is not in the bottom category finally, which means it's in the top category, so that's good. You guys wrote in the sulfur column, right? I made you guys do that one day, right? So I don't have it on my table here, but if I remember correctly, this one actually, the iron would be in the bottom category, so that does fit. And then this is a nitrate right here, I think. I hope it's nitrate. It should be NO3. And iron would be in the top category. So iron actually fits for all of them. So iron is the one that should have worked, I believe. If you wanted to, you could go through and do silver as well. But I believe silver fails on this one right here. When you do silver with SO4, it should have given you a solid. And this one right here clearly does not give a solid. There's a lot to interpret on that question, hey? All right, one more, and we'll take a break. Another math question. We're being asked to work with formaldehyde, which I give you its formula up here. And we've got liters and moles per liter, and we're looking for kilograms now. So I would recommend start with something like this. 3 liters times it by the 11.6 moles per liter. Why did I just randomly choose to do that? Well, I got rid of liters. That's good. What am I left with, though? I don't want moles. But hopefully you remember my analogy of like donuts. This is like, we just need to figure out how heavy are my donuts. Or in this case, how heavy is formaldehyde? If I can find a molar mass, I can cancel that moles away. So I just need formaldehyde's molar mass, which is 1.01 twice, 1201, and 16. Thank you. Save me some time there. 30.03. Times this, times that, times this. If you wanted to, you could divide by 1, I guess. Because it is like moles per 1 liter, grams per 1 mole. But the dividing by 1 is kind of redundant. So let's try this. 3 times 11.6 times 30.03. I get a big answer. 1045044. Good. So there's the next twist here. Is not only did you have to get this in grams, you got to make it kilograms. That means you got to divide by 1,000 by bringing the decimal place over a few times, which makes it 1.045044. And then getting sig digs right, you only get 3 sig digs. So it's 1.04, except this 5 right here rounds it up. So the correct answer should have been 1.05. How are we doing so far? In hindsight, after me giving you some answers and walking you through this, is this something you guys can do?
Yeah.
Michael can, at least. Thank you for saying something. Is this something you guys can do?
Yeah.
Okay. The issue then, and this is, I make it sound so easy, but the issue is execution then. You can't make dumb mistakes. Stuff that you know how to do, or that you have the skills to know how to do, you can't screw those ones up. Because you will come across questions that like you just don't understand, or that you don't, does that make sense? There'll be those ones. The ones that you should be able to get, you gotta find a way to start not screwing those ones up. But like I said, I make it sound so easy, just don't make mistakes. Wait, go take a 5-minute break, and then we'll do the second half of the test when you come back. Okay, the next 3 questions, they all go together, and they all involve the exact same stem of the question. One of them asks you for like weight over volume, one involves parts per million, and the last one involves moles per liter. So let's try to go through these ones here. If we want weight over volume, you need to find its mass, divide by its volume, and times by 100. That's it. That's all you're going to need to solve it. The only problem is when you do this particular example, 110 divided by 125 times 100, you get 88%, which is not one of the 4 answers. Think about that for a second. 88% concentrated. I mean, 88%? Doesn't that seem a tad excessive? Okay. You're not doing it wrong. It's just one of your units wasn't right. You didn't want it to be in milliliters, I believe it was. You wanted it to be in liters. No, wait. It needed to be in grams right here, not milligrams. So rather than making it 110, make it 0.110 grams in 125 milliliters times by 100. And now you do get an answer. It's the 0.0881. Or maybe if you did this at first and you said 88%, that's crazy high. I mean, the only one of these numbers that involves those same digits is that one there. It's just 1,000 times different because one of the units was off. That makes sense? Okay. So in addition to doing things in weight over volume, you can do parts per million. And this one's probably the easier one of the two. Parts per million is a milligram in a liter. So on this example, we knew how many milligrams there were. There were 110. Liters, we didn't have it in liters, but I can convert by just dividing by 1,000. And actually, that's all there is to it. Take the two numbers and just divide the two. Just make sure your units are in milligrams and liters. And this one still involves eighths. It's just now it's 880 parts per million. Do those two questions make sense? Really, you're just taking two numbers and dividing them. One of them you times by 100, the other one you don't. Just all you got to do is make sure the units fit. So, this one's probably the most challenging one of the three. This one now wants moles per liter. So, in order to get something in moles per liter, we need to get a mole number, and we need to divide it by a liters number. And we have the liters number. The liters number is 0.125. The problem is we don't have a moles number, but there is a way to convert it. If we have grams, we can use a molar mass to get to moles. So there was supposed to be 0.125 grams, I believe. No, that's not right. It was 0.110 grams. Yeah. If we can use a molar mass number, we can then get an answer in moles, and then that number will go up here. That makes sense? So how do I find a molar mass? Yeah, add them all up, which I hid way at the top here. The formula for caffeine is carbon times 8, hydrogen times 10, nitrogen times 4, and oxygen times 2. Just don't screw up, right? Like, just make sure you can get that number without mistyping something. $194.22. Okay, 194.22. Where does that number go down here then? It goes on the bottom. It goes with the grams. There are 194.22 grams in this mole of donuts. Right? 1 dozen donuts, 1 mole of donuts weighs the 194.22. So you're not actually multiplying, we're actually dividing. So take 0.110 and divide by 194.22, and my calculator spits out this number, 5.66368 E minus 4. Anyone else try that in your calculator? Get the same thing? What does this mean? What does this E thing here mean? Times 10 to the minus 4. So like if you wanted to write this number out, it means 0.0005666368 because the decimal place has been moved over 1, 2, 3, 4 times. So it's a very small number. Is this my answer though? What do I still have to do? I still have to divide it by the, like that's my mole number. I still have to divide it by 0.125 liters. So divide by 0.125. And now my calculator spit out this number for me, 0.00453. And so on. How do I write this then? Do you see how right here I mentioned that it was going to be times 10 to the minus 3? Well, move your decimal place over 3 times then. Move it over 1, 2, 3 times. This is now 4.53 times 10 to the minus 3. So what I was expecting you guys to write then was this, 4.53. That one's a challenge. Anybody get it? Okay. Can you get it now? Do those steps make sense? All the little twists and turns and stuff you have to be able to accomplish? Because there was a lot that happened here, right? You had to be able to get correctly a molar mass up top. You had to be able to get that number. If that number is wrong, you're screwed. You had to be able to interpret, how do these numbers go together? So you had to understand, well, divide these two numbers. You had to get that part. You had to understand what this thing right here meant as a number. You had to know that you had to divide it again by a liter's number. And then maybe even if you got that far, you had to be able to interpret, well, 0.00453, I still have to move that decimal place over 1, 2, 3 times to even get the answer the way it needs to be phrased in the, like this little bit right here. That makes sense. I think what you guys will discover is that sometimes there'll be like 1-step problems, and sometimes you'll get like 3 or 4-step problems. And this is one of those 3 or 4-step problems where you have to do a lot of little things right to get it right. Questions? Okay, moving on. Last thing, still the same stem. We want to talk about caffeine, and we want to talk about sugar. Caffeine, I gave you guys the chemical formula for caffeine. I mentioned it was an organic molecule. That doesn't probably mean much to you. Tell me something about the chemical composition of caffeine. It's molecular, yeah. You guys catch that all of these things up here are nonmetals? Molecular things. Should they conduct? They should not. So therefore, caffeine should be a non-electrolyte. That's the first blank. And then the second half of the question is, what about sugar? Well, what is sugar? Anybody know anything about sugar's molecular formula? I mean, sugar can be like, say, sucrose or glucose or something along those lines. C6H12O6 or C11H. You guys know what I mean by that? Well, is that ionic or covalent? It's covalent again. Yeah, sugar is a covalent molecule. So covalent things, again, do not conduct. So like sugar, if you want to write out its formula, it might have been like, say, C6H12O6. Or maybe C11H22O12. I don't know, whatever those formulas are. I don't even care what the formulas are. All that matters is those formulas do not involve metals and nonmetals. They're all completely covalent. Does that make sense? So it means it's a non-electrolyte. So the only category that fits both is A. By the way, this would be the kind of question where if you want to choose more than one answer, it might not be a bad idea, so long as you are dead certain that you know half of it. Does that make sense? Like if you didn't know anything about sugar and you just did not know about the second column, but you were dead certain that caffeine was a non-electrolyte, then you could pick A and C and at least get half a mark. But just make sure that you're certain. One piece of advice I might give you is look at the counting, the total along the bottom. If the column for which you get half marks is not outweighing the column for which you lose marks, you should stop picking 2 answers. Does that make sense? Because it's not helping. You know what I mean? Like if you got like an extra 2.5 marks for the partial column, and then you lost 6 marks for the wrong column, it's probably not a good idea to keep picking 2 answers. Okay, dissociation. What does dissociation bring to mind? What does it mean? Sure, it has to be something that's ionic. It needs to split up into positives and negatives. That's dissociation. So let's walk through these. CaF2. Yeah, we got a positive and a negative. There is a problem with this one, though. There should have been a 2 in front of that F right there. Does that make sense? So that's why A is not right. B does get split up into positives and negatives, but it gets split up into a couple of positives and a negative. That doesn't really fit. This guy right here should have been an OH minus. then you have a cation and an anion, so that's why B is out. C is also out because it's not ionic. Yes, there's a negative and a positive, but this thing right here is not a polyatomic that we would seem to recognize. This involves all nonmetals. So this guy's covalent, so that one's out. So D is the only one that actually seems to fit. A lot of them are kind of close, but for one reason or another, there's something wrong with A, B, and C. That make sense? All right. Kind of similar question. We got to kind of walk through all 4 of these and make sure that it fits. We want to check these properties. Copper 2 full sulfate. That's an ionic compound. Ionic compounds should conduct electricity, so that's out. That doesn't fit. Lead 2 iodide. That's an ionic compound. So it should conduct electricity. That's good. But should it be ionized? No, ionic things dissociate. So that's why this one doesn't really fit. We just talked about this one 2 questions ago. Sucrose, sugar. Sugar is a covalent compound. Covalent compounds do not conduct electricity. So that's out. So this is the only one left that fits. Let's test it. Sodium nitrate. That's ionic. Ionic things do conduct electricity, and ionic things dissociate. Did they get that one right? Pretty good for you guys. It's one of those ones where you kind of got to walk through all of them and make sure you catch all the little details. Because like B is close, except it doesn't ionize. And C is close, except sucrose should not conduct electricity. Actually, it doesn't dissociate either. Okay, this question here, first you need to be able to interpret what I'm saying is happening here. So imagine you've got a solution. So I'm just going to draw a beaker, and inside there's a solvent. And it said it's saturated. What does saturated mean? It means it's full. Okay. We have put a lot of solid stuff inside. We've added some solid crystals. It doesn't have to be solid, but it probably is solid. And this solution is full. So full that it just has an excess precipitate. What does that mean? It means you've got like stuff along the bottom here. I probably shouldn't have called this saturated. I probably could call it oversaturated. Basically, I've described for you an oversaturated solution. Does that make sense so far? Okay. For what? Just like everybody? Can I keep talking while you take pictures?
Yes.
Okay, we'll do that then. If you guys are okay with that. Okay, so you guys see how like there would be something sitting on the bottom? Okay. In one of our slides of notes, I talked about the idea that it's not just sitting there. There is actually stuff happening at a microscopic level. What's happening is this solid stuff right here is breaking apart into pluses and minuses. But other pluses and minuses are recombining into solids. We had a name for it. Do you guys remember the name for that? Begin with E. Begin with equal. Yeah, it's called equilibrium. Do you guys recognize that term at all, equilibrium, from our notes?
Yes.
This is an equilibrium system here where the solid stuff in the bottom here, it's not just sitting there, it's breaking apart. Water molecules are saying, hey, there's more solid stuff, let's rip them apart. But then those water molecules that go rip apart that other solid are no longer able to keep the other particles apart, and so those ones go back together. Does that make sense? Now, do you see anything? No. But if we had like a super awesome microscope, you would see all sorts of interactions happening. So equilibrium will have equal rates of dissolving and crystallizing. This stuff right here is dissolving. This stuff right here, the ions that were separated, are going back into solid form, crystallizing. And here's the key. At equilibrium, it'd be the same. That makes sense? In order to get that question right, though, you had to remember the idea of equilibrium. So like, hopefully that's something you recall from your notes. Any questions on that one? Okay. Okay, math question. Really key word here. We are diluting. I wouldn't say like always, but if I see the word diluting, it probably should bring to mind the idea that there's a formula for diluting. C1V1 equals C2V2. So hopefully when you saw that word, you thought, okay, here's a formula I can use. We just got to put numbers in the right spots. This right here is a 1.25 mole per liter, and it was 50 milliliters. The second concentration is 0.25 moles per liter, and we actually don't know the second volume. Does that make sense? So divide by 0.250. Divide by 0.250. And I think when you do all of that, you get the answer 250. But that's not the right answer. And it's sneaky, and you gotta read oh so carefully here. It has one word right here. The question is, how much water should you add? You already have 50 milliliters. And this right here is the total. So you want a grand total of 250, but you're starting with 50. So how much water do you add? You only add 200. It's slight. Does that make sense? That word right there is very important. But it makes a huge difference, right? If we went into a lab and you did this calculation and you added 250 milliliters of water, you were now no longer accurate. Does that make sense? Because you did it incorrectly. So you have to understand how this formula works. This volume right here is the final total volume. So if you want to figure out how much more you need to add, subtract what you started with, because you already had 50. It is tricky. That being said, now that you've seen that, don't make that mistake again. Does that make sense? Learn from your mistakes. So, not 250, 200 is the right answer. How many of you picked 250 out of curiosity? Okay, so you have some knowledge for sure, right? It's just the details. I said that a lot in math, actually. At this point, for like the next however much longer you want me to teach you, that's something I'm probably going to be harping on, is you got to watch the little details, because that's what makes the difference, right? Okay, this one was for like the next 4 questions. I think we're starting out with a math question here. We want to figure out grams. So if you haven't kind of picked up on how this works here, we're going to need to use a molar mass at some point to get grams. And these numbers right here will probably be useful as well. So I'm going to start with these ones. If we have 0.16 moles per liter, because that's what capital M is, that's kind of helpful, but I don't really want per liter. So I'm going to times by my liters and make it 0.100 liters. I'm going to convert this guy by dividing by 1,000. There. Liters is gone. Halfway done. Well, kind of halfway. By the way, if I change the order of these numbers, is it really impacted? No. But if you like my donut analogy, we now have moles. So it's like you go to the store and ask, I want a dozen donuts. But they ask, well, how heavy are they? We need to know how heavy these donuts are. So we need a grams per mole number for lead 2 nitrate. So what's lead 2 nitrate? But it's NO3 with a 2 afterwards. The slightest detail is going to screw this up. If you forgot that 2, you're hooped. Because it makes all the difference, right? So let's see. I believe lead is 207.2 for lead. Nitrogen is 1401. We need 2 of those. That's nitrogen. And then oxygen is 16 on the dot, and we need 6 of those. What'd you get? 331.22. Anybody else get that? Sorry, was that? Yeah, okay. I just always like to confirm with kids in the class, because there's nothing worse than someone does a calculation, they make a mistake, and then we do all of our work, and it's the wrong number. So if that is 331.22, then hopefully you can visualize. This liters will cancel that liters. This moles will cancel that moles. What's the only unit I have left? Grams. So multiply. 0.16, 0.100, and that 331.22. I got 5.29952. But then for sig digs, you only get 2 sig digs, so hopefully I had 5.3. Okay, some theory then. This actually goes right back to the very first question we asked. I'll tell you the answer. The answer is a standard solution. Things that have exact concentrations, if we know its concentration, the term we use for that is standard. We know it. It's not uncertain to us. We know that the concentration is 0.16. That is a precise number. Precise. So it's just a definition you need to know. Exact solutions are known as standard solutions. What are stock solutions? Highly concentrated. Good, yeah. Saturated solutions? They're full. Supersaturated? They're more full than they should be because we've increased the temperature. Okay, we've done a question like this before, earlier in the test. But I'm guessing if you got that one wrong, you probably got this one wrong too. This is lead nitrate. As it dissociates, it'll dissociate into lead and into nitrate. However, I haven't written this question perfect. I've made a mistake here. Anybody know what my mistake is? It's not balanced. There should be a 2 in front of the nitrate. What this means then is that if this guy right here is 0.16 moles per liter, the nitrate, this is a 1, that's a 2. So this is my daughter playing with Lego. She has one big Lego toy, and it takes up 0.16. And then she breaks it into pieces. Well, now that there's 2 pieces, it's twice as concentrated. So now it'll be 0.32, because you've doubled. Out of curiosity, anybody get that one and the one earlier in the test? Okay, I will say once in a while that sometimes when kids do poorly on a test, sometimes it's not because they don't know how to do the whole thing. Sometimes the same question comes up more than once on the test, and I would gather that if you got it wrong the first time, you probably got it wrong the second time, unless you guessed, right? But if you knew it, hopefully you got them both right. So one thing I'd advise then in your progress logs, if this was the kind of question you got wrong, that's something that you can improve on for next time, right? That's an improvement to make is next time we do one of these, something ionizing, and all you got to do is times by 2. Now hopefully you'll recognize it. Okay, this guy right here, we need to write an equation. It needs to be lead nitrate plus calcium carbonate. And we want to see what it turns into. And either way, it turns into lead with carbonate and calcium with nitrate. The question really is, what are these coefficients down here? Like, is it a solid or is it an aqueous? So there's not really much I can add to it other than know how this table works. If you know how it works, you probably got it right. If you don't know how it works, talk to me. So looking at the table here, carbonate and calcium looks like it's a solid. And lead, calcium and nitrate looks like it's an aqueous. And lead and carbonate looks like a solid. So that one, solid then aqueous. Did I do that right? I don't have much to add on that one. You just have to know how to use your table. If this table doesn't make sense, so you got it wrong, talk to me later. All right, moving on. We need another math question here. Our goal now is to get to liters. That's going to change things for us a little bit. I want to show you a wrong way of solving this question. Let's say you write 15 moles per liter, and you try to write that down like this. Do you see how liters is on the bottom of your fraction? That's not helpful, because we need liters to be what is remaining when we're done. So at some point during this example, you're going to want to flip this thing upside down and make it 1 liter over 15 moles. We're going to have to flip this ratio upside down. Guaranteed, at some point you need to do that. I don't know whether that's the first thing you want to do or the last thing you want to do, but you have to flip this guy upside down so that liters is on the top. Does that make sense? Herein lies the problem then. I need to now get rid of moles. All right. Here, I'll just write moles on top. That'll cancel it.
Sarah Beebe and Coleman Crawford-Wolf, can you please come to the office?
I have to put something on the bottom though. I can't just write moles up top unless I have a moles number. So fortunately though, we can use moles and grams. I can find a molar mass. And I can maybe use that, because now that will cancel out the moles. The problem now I have though is that grams is on the bottom. I don't want grams on the bottom. But here's a number I can use, 200 grams. That one doesn't even require a ratio. I could just times by 200 grams. You see how those grams would cancel then? That's kind of the stem to the equation. You need to take this guy right here and flip it upside down so that liters is on the top. To get rid of moles, you'll have to do moles and moles here. Grams will have to go on the bottom. But fortunately, this grams can cancel with that grams. I need a number to go here now. So where do I find a molar mass number? Okay, so a couple of things. In order to solve this question, you need to know what phosphoric acid is. Well, it's going to involve hydrogens and phosphates because X turn into 8s. And because phosphate's a 3-, you need 3 hydrogens. So that's phosphoric acid. If you can't do that step, the whole rest of it's going to fall apart. Eh? So now molar mass. So you need hydrogen, 1.01, you need 3 of them. Phosphorus, I don't think I have memorized right now. Thank you. 30.97, you just need 1 of them, and then 16 times 4. It's 90 right on the dot, isn't it? That makes sense so far? A lot of skills you need to solve this question. You need to know what phosphoric acid is, because if you don't have this written out properly, you're screwed. You need to be able to do the molar mass, and then in addition to that, even, you still need to know where this number goes. Where does the 98 go? On the top of the fraction or the bottom? It goes on the bottom. Good. The reason why is that that's how many grams are in your mole. So I like that donut analogy. 98 grams is how heavy these donuts are when you have 1 mole. So now for your calculator, here's what I'd type in. Go 1 divided by 15 times 1 divided by 98 times 200. So I'll even write it out. I did 1 divided by 15 times 1 divided by 98 times 200. And I got 0.136. With sig digs, that makes it 0.14. That might be the hardest question on the test. I would say you guys have these skills because we've worked on them. I know we have. We've done them even in this test. But being able to put all of those skills together in one question and not make any mistakes, that's tough. Does that make sense? Okay, 2 more. This is another challenging question. You need to use information in your data booklet. There was a chart that you're supposed to flip sideways that I would have talked about one day. Do you guys remember this sideways flipping chart? There are 6 acids that we know of that are considered to be strong. They're all the ones above the top line there. And if you list for phosphoric acid is actually not one of the 6 strong acids. So that must mean that it is a weak acid of some kind. Does that make sense? How do you tell whether it's concentrated or dilute? Well, that's based on that number right there. 15 moles per liter. Pretty high. Does that make sense? So therefore it's a weak concentrated acid. Weak, because in your data booklet it's not one of the top 6 on that table. Concentrated, because 15 moles per liter is about as concentrated as something can ever be. I can't make it more than that. Okay, and last one. This is another matching kind of one, very similar to the very first question. I'm going to give you 6 statements. You got to figure out which ones are necessary. So let's talk through this. When you make a solution, the first thing you should do, you should go to the scale and weigh it out. And that's number 3. Go to the scale and weigh out some crystals. Those crystals, though, cannot go directly in your volumetric flask. Like number 6 right here, put the solid crystals directly into the volumetric flask. You should never have used number 6. Why? Why do we not put crystals directly into a volumetric flask? Because you can't stir them in there. It's just not practical. So instead, dissolve the crystals of lithium nitrate in a small volume of water by stirring. Do that instead. Then add the solution to the mark and add water to the flask. And then finally, cap the solution and invert it to mix. Number 4 here, stir the solution inside the flask with a stirring rod. That's not possible. Stirring rods don't usually fit inside volumetric flasks. So hopefully the 2 things that you didn't use were 4 and 6. And you got the other ones in the right order. All right.